Okay, we are going to continue from the last video. So hopefully you had paused that other one, or you can just put it to the side. We're going to continue with beta radiation here. This is the second type of radiation. It's called beta. I'd like you to write the symbol for it over here. It looks like this. It's got like a capital B with like a little tail that comes down. Okay, that's capital beta in Greek. It's a fast-moving electron. So we are going to look at electrons here formed by the decomposition of a neutron of the atom. The net effect, the neutron actually changes into a proton. So what happens is a neutron that has no charge turns into a positive proton. So it's positive. And what happens is what's released is a negative electron. Okay. Much smaller than an alpha particle, which means it's actually more dangerous. So here's the symbol, capital B with the lower little tail. Charge is -1, okay, -1. Much more penetrating than alpha particles, which means it is more dangerous. It can be stopped by something thicker. Remember, alpha can be stopped by paper, but beta needs something a little stronger, like aluminum foil, okay, or a thin piece of wood, really. But something thicker than just a small sheet of paper, all right? So here's a picture. Let's check it out. Here's cesium, okay? You'll notice that it is less than 84. So this is considered a light nuclide. And what we're going to do is, you'll notice that the mass number is not changing. Because remember, only a neutron is changing into a proton, which means the mass does not change. So I'd like you to write that. For beta, the mass does not change. But what does change? The number of protons. It's going to go here from 55 to 56. And why did that happen? Again, the neutron turned into a proton. The bottom number on these guys are the protons. So if we've turned a neutron into a proton, the mass doesn't change, but the atomic number does. So the mass does not change, the atomic number does. The atomic number changes. Okay, so let's look at these examples down here. Let's look at the first one. I'll change to red. The first example. Carbon goes through beta radiation. The mass stays the same, does not change. The number of protons increases. One of those neutrons changed into a proton. Now, I want you to look at this. This is the beta particle. Remember that the alpha particle, so alpha was a helium atom, He42. It had 2 protons, 2 neutrons. The beta particle, I want you to write this in, 0, -1, and it's got a little E for electron. That's what it means. It means electron. Why -1? Because electrons are negative. And if that represents a proton, it's the opposite of a proton. It's a negative. How about the second example down here? We start off with a single neutron here. The mass does not change. The protons goes up by 1. And we form a beta particle. Those are your beta particles here. How can we label these elements? Well, you look at the atomic number. If it's 1, it's a hydrogen. 7, it's nitrogen. So that's beta. And we're going to practice this too. Okay? So reference your notes if you need some extra help. Number 3, gamma. Gamma emission. Okay? Gamma emission. Electromagnetic radiation. This is going to be a high energy. So, yes, the Hulk was exposed to a high amount of gamma radiation. So if you're an Avengers fan like me, Hulk is totally my favorite superhero of all time. Unfortunately, you can't just go expose yourself to gamma emission and become like the Hulk. That is total science fiction. But it is high energy, emitted from a nucleus as it changes from an excited state to a ground state. So with this one, I want you to write something. There is no particle. Physically, there's no particle, but there is energy, and that's what we're after, okay? Here's the symbol. It looks kind of like a letter Y almost like an alpha particle that was flipped. It's got kind of like a little hook. We call that gamma. Almost like an R. Yeah. And then remember that beta is like that. Often emitted along with beta or alpha. So sometimes gamma can be a side product of the first two types of radiation we learned. The symbol, it's like a capital Y. I like to add the little hook, maybe a little swish. Kind of like you're drawing birds, maybe like, you know, as a kid, you draw those little birds, something like that. It has a charge and no mass. It's energy, but it's not a particle. High energy photon. So this is kind of where light comes from. And remember that we have the electromagnetic spectrum. We learned this thing that goes like this. And eventually we have these high energy waves. Well, these would be like gamma. Okay? High energy. It's a part of the electromagnetic spectrum. Extremely penetrating and very dangerous. Okay? These are probably the most dangerous. Stopped by several feet of concrete or several inches of lead. So when you hear of radiation poisoning, a lot of times gamma emission does that. Okay, so several feet of concrete, also several inches of lead. When you go and get an x-ray, they protect you from this by putting a big lead vest on your chest. That's how they protect you. Let me erase this real fast. Okay, so let's check out the picture. Plutonium. What does it change into? Plutonium. Okay, but remember, no particle is lost, but there is radiation. So really what you would show is that there's an added bit of radiation. You could even call it 00 here. It's high energy electromagnetic waves, gamma. No Hulk, but very dangerous. Okay, and last but not least, we're going to call this one positron emission. Positron. It's a particle with the mass of an electron, but with a positive charge. So, positron, almost like a proton, and if that's what you want to write, go ahead. It's basically a proton. Mass of an electron, so it's smaller than a proton, but it does have a positive charge. So here's the symbol. Let's go through them again. An alpha particle, 4,2, that's helium. A beta particle is 0, -1. Oh, that's terrible symbol. Let me fix that. Gamma radiation is 0, 0. And here we have positron, 0 and +1. So you'll notice that it looks a little bit like beta, but a little bit different. We call it antimatter, also known as dark matter. So yes, we're talking about like black holes and whatnot, which gets crazy awesome, and that's something that you'll start to learn about maybe in physics or astronomy. But for now, we're just going to focus on the emission, the radiation. So let's go back. Let's look at this. Let's look at this example right here. This is positron. Here's your positron particle. Here's neon, Ne. The mass stays the same. 10 plus 1 gives you 11. So everything makes sense. Atomic number 11 is sodium. Okay, let's sum it all up. We are almost there. Type of radiation. So here we go. There are 5 listed here. Here's the first one, alpha, beta, gamma. Now, neutron, we didn't cover. You may see it. We're going to talk about it briefly here, but those are the 4 that you really need to know. Here are the symbols, alpha, beta, gamma. Positron, we actually give just the letter E, but remember, it's a +1, beta is a -1. It doesn't have a fancy Greek symbol. Neutron emission is what it says. It's just a neutron. So let's go through them. Here's the helium atom, 4,2. Here's the beta particle. Here's the gamma emission. Here's the positron, and then let's look at the neutron real quick. Well, it is what it is. It's a neutron. Doesn't have a charge. It's neutral, but it does contribute to the mass number. So, penetration. Alpha, low penetration, not so dangerous. Beta, medium, needs like aluminum foil or a piece of wood, something thicker. Gamma, high penetration. Okay, you need concrete, basements, lead vests. Okay, neutron, very high. It's actually very dangerous. We're not going to talk about that a whole lot, but positron is medium, probably about the same as beta. Remember, the particle is about the same size, but this one's -1, this one's +1. Okay, so let's look at the danger levels again. Alpha can be stopped by paper. Beta has traveled through paper but can be stopped by plastic or aluminum foil, something thicker. Gamma can be stopped by lead. Okay, neutron, probably the most dangerous out of them all. They can actually travel through concrete, but it's not a charged particle, but it can penetrate through really thick substances. When nuclear power plants were first developed, people thought they could protect themselves from a nuclear blast by hiding in their basements. Was this a correct assumption? Well, nuclear blast, it depends on what type of radiation it is, but so far we know that basements are made of concrete. So can concrete stop all the types of radiation that we talked about? The answer is yes, it was, and people were safe if they hid in their basements. So we're going to practice writing nuclear equations. So here's the first one. Cobalt goes to nickel, and what we got to do is fill in the missing blank. So what's missing? 26 plus what gives you 27? Well, it's going to be a +1 there. The mass doesn't change. +1, this is going to be a positron emission. Okay, how about this one? This one's called americium. It is atomic number 95. I knew that because I looked on the chart. I don't know the mass number. Neptunium, Np, is atomic number 93 if you look on the periodic table. Now, I don't know the mass. That's what I have to figure out. So, it goes from 95 to 93. I know that that's a difference of 2. And the only particle that has 2 is this one, 2,4, which is a helium atom. This is alpha. Positrons up here. This is alpha down here. So now we can fill it in. Neptunium versus americium. And I'm going to go ahead and give you neptunium as 237. We're going to provide you one of them. You have to know one of them. 4 plus 237, that's going to be a 241 for americium. Okay. Thorium goes to helium. So we know this is a 4,2 alpha. This is another alpha particle. But we don't know what it forms. So let's look at thorium. Thorium is element number 90. We don't know the mass. Okay, but we know that it's going to drop from 90 by 2, so it's going to be element 88. Element 88 is going to be letters Ra for radium. Okay, and we're going to go ahead and give that a 226. 226 plus 4. Thorium is going to be 230 here. We're going to have to provide you one of the mass numbers, so don't fret about that. Okay. And the last one here is going to be nitrogen plus something yields carbon plus a hydrogen atom. Well, this one you kind of have to think critically. 6 plus 1 is 7. 7 plus 0 is 7. So this one's actually that one that we didn't talk about. 14 plus 1 is 15. 14 plus what gives you 15? Well, it's going to be a 1. Well, on the chart, that's going to be a neutron radiation. And that's going to finish notes for today. So what I want you to work on is worksheet number 1. Let's practice writing out nuclear equations to show the radiation. Okay, best of luck. We'll see you tomorrow.